5, etc. Negative parts are not allowed. We disregard, okay? We only assume positive roots. To find the positive roots, of course, the given number should not be negative as well, okay? It should be a positive number. So these issues will be given as a message in the beginning of the program. Hey, give a value greater than this, less than this, satisfying this condition, the program will calculate its square root, whatever. So square root of s is the given number. So you first start by an initial guess. It can be anything. You start with 1 or 10 or 100 or whatever, okay? But this program is utilizing a byte value, maximum 255 positive. So its square root does not exist, probably 17 or so anyway. So you can estimate by 1 any positive number. You should not start with 0, but you can estimate any number. Improve the guess by applying this formula. This formula is, this is your guess, and this is the ratio of the given number to your guess, and it's divided by 2. So there's a mathematical addition. Well, first of all, a division and then addition and another division exists, okay? So this gives the second estimate. So x1 is, according to Babylonian method, is a better approximation. Then you use this x1 to obtain x2. So this is the so-called iteration formula. It's the iteration the iteration n plus 1 is obtained by using iteration n. Whenever these numbers are equal, of course, the iteration ends because you cannot continue till infinity, okay? You have valuable time for the computer. Convergence is achieved when the digits of n plus 1th iteration and nth iteration agree to as many decimal places, okay, as you desire. And you can also reach details of this method to this internet site or some other similar internet sites, because this is a very well-known technique. Now, before designing the program, of course, let's have a try. Calculating the square root of 20, for example, also given at the website of the Babylonian method. The initial guess is assumed to be 10, so its square is 100. So, well, of course, this is a, let's say, too high guess, okay? So the next guess with that formula is 6. So 10 goes down to 6, which is a better approximate, but this is still high. So the other guess is this, okay? So after each iteration, okay, there's so-called conversion to the square root. You see, starting from 10, 6, 4.66, 4.5, etc., it's slowly approaching. If we continue further, as many steps as we go, we come closer to the square root of the real square root of the 20, okay? But we can stop at any moment. We can say that the square root of 20 is between 4 and 5. Why? Because 4 is 16, 5 is 25, 20 is in between. But how come? Okay. So 4.5 is a nice guess. Or 4.4 could be a better guess, etc. It depends on your precision. The actual guess can be obtained with 2, 6, 8, 9. Sorry, 2, 2, 4, 6, 8, 9. Yes, 9 decimal places. Well, this is not the real square root. Of course, it continues, but up to 9 decimal places, we can calculate. How did you find this number? Okay, of course we cannot find this with our microprocessor. Okay, that could be a very long program. Okay, because those many fractional digits require many memory allocations and other things, conversion of the fractions to integers, etc., will require lots of memory space for code and data. So it's a really not a good idea to write a program to calculate that much. This was calculated by using ordinary office program. Okay, so in Excel you can create that formula, and in a couple of minutes time, etc., you can uh, see the iterations and reach that result. Okay, so any calculator, well, any calculator, your smartphone calculator or other calculator, etc., they are utilizing similar formula to give the result to you in, let's say, 8 digits, 8 fractional digits or more, etc. Okay? By these kind of approximate methods, they don't give exactly perfect result. Okay, so in that program, of course, that was the test of that iteration. Okay, whether this method is proves to be useful, and it's proved for 20. You can also utilize for other things. Now, look at the flowchart of this example. There are some assignments. The given number is stored in DL, and initial guess is stored in BL, and iteration loop starts from here, continues, and then returns back. Okay, so that's a part of the flowchart actually. So what you do is, first of all, you store the number to AX for division, and you divide with BL, because we have to first calculate this value, S over X0. So this part calculates S over S0, X0, sorry, or S over the initial value, whatever. Then it's added with X0, or the iteration estimate, or the iteration. You obtain the numerator part of the expression. Then you divide it with 2 to obtain the next iteration, and then you change the values in the registers accordingly. So the registers actually, especially BL, carries the most recent iteration. So XN resides in BH, XN plus N1 resides in BL, in short. So B register stores as byte values of both iterations, the obtained or next iteration, n plus 1 iteration, as well as the previous iteration. So the command used, of course, is division command. Well, everybody is very familiar with this command. This is the functional information of the command for our purposes. So we are continuing to find the flowchart and converting to assembly code. And in the iteration process, we have to check whether the convergence is achieved or not. So if both iterations, I mean, most recent iteration and the next iteration are equal, of course, there's no difference in terms of integer-wise. There's no difference between the iterations, so the convergence is achieved. So for our problem, where there's no fractional part, we only deal with integers. If remember, BX register carries the most recent iteration and the next iteration. If they are equal, That means there is zero difference between the iterations. Perfect iteration is obtained. If they are, of course, not equal, then we have to continue the iterate. In order to have positive number after subtraction, perform subtract. Okay, so actually, the let's say absolute value here is required because we don't want to deal with negative numbers in our programming case to be simple. So we have to check numbers. So for the initial the guess of 20, we are always going down. So our iteration, next iteration is always lower than the previous iteration. So in order to avoid to have negative number, we have to subtract BL from BH and store BH. That's a positive number. So here's the flowchart. If the test is BH and BL are equal, zero flag should be set. And as soon as they are equal, zero flag is set, then convert means that convergence is reached and the program should end. Of course, you can put some messages, some screens saying that the square root of the number is this from by using the value in BL, etc. They are omitted here and means that's consisting of all the sub procedures for output messages, etc., and termination of the program is included. And if not, if they are not equal, then BH should be revised for the next iteration. Okay. If the difference BH minus BL is 1, then convergence has also been achieved. Why? Because, as I said, the square root of 20 is between 4 and 5. Okay, so if your iteration gives 4, the next iteration will give 5. If the iteration is 5, the next iteration will be 4, because only the only the integer values close to the target, and you may observe some oscillations in the iteration. Anyway, those are details, and they can be modified as well. So every time you check with the register BX for iteration convergence. So the assembly code of the flowchart will be as follows. It's just writing the required code for each little box in the flowchart. Okay, so and the commands are written in mathematical language here. Okay, so these 3 lines calculates these parameters and iterations, etc. And these are the end of the code statements. Okay, so iteration. If the result is 0 or 1, then it will be stopped and the program should end. Well, I have not included the screen version, but I have tested this program in my lecture room. So it's also given to you as an exercise to test the program in the emulator environment. Another program. Okay, these programs may be your final examination homeworks to find some trigonometric results, to do some calculations, to do some complex real number operations, okay, not integers. So those are good starting examples. Also, emulator 8086 has similar example codes, but definitely they will not be included in the midterm. Okay, those are the issues later on. So to write a program to calculate cosine of a given degree in decimals. And of course, degree cannot be higher than 255. So we just set limits of between 0 and 180. Actually, 0 up to 90 could be even fine. And which should be correct up to 2 digits after the decimal point. Why? Because cosine gives values between 0 and 1. Okay, for integer operation microprocessor, you cannot have all the cosines of the degrees between these numbers, but you can express them 2 digits or up to 100. That's the reason 2 digits, up to 100 after decimal point. Now, one way of solving this, expressing all the mathematical formula as a Taylor series expansion and inserting the Taylor series expansion center point or around point, angle equals to 0, because angle 0 has very fine coefficients, etc. Then your expansion could be very simple, related to the problem. Also, there are some exercises for those are interested in those topics. These exercises are related to the other real valued functions, like trigonometric functions or logarithmic functions or base 2 logarithmic functions as well. Well, of course, these are left as an exercise after the midterm. So that's all for today. I will also include those slides to our website, and I can answer your questions accordingly if you have any. If not, okay, could I ask 2 questions, Görkem?